Okay, good afternoon, everyone. I hope you can hear and see me clearly. Well, not see me, see my screen clearly. Um, we're just going to wait a few more minutes in case anyone else wants to join, and then we will begin the webinar. Okay, welcome everyone. Today's topic for the webinar is Inventor Joints and Constraints. It's mainly to deal with relationships in assemblies and how you can better use the tools and understand the difference between each of the types. Okay, um, we are joined in by TeamViewer, and I believe TeamViewer has changed with its interface. So you just want to familiarize yourself with the where everything is in case you want to ask any questions. There's a little chat box icon on the bottom, so you're free to type in your questions during the webinar. I will answer them during the webinar, or if not, if I miss them, I will take a look at the end. We do reserve some time for a Q&A session at the end of the webinar. Okay. Also, we will be recording this webinar, so you can watch it later if you have to leave early. So that's not an issue as well. And okay, let's dive straight into it. Okay, let's just discuss our agenda for today. First, we're going to just chat a little bit about me, who I am, what I do, and talk a little bit about micrographics. We're going to discuss the purpose of this webinar and why I decided to do it. Then we're going to get into the technical bits of joints versus constraints. We're going to talk about the assemble function. Then we're going to do a live demo of constraints and joints. Okay, we're not going to dabble too much into how to make an assembly. We assume you have some knowledge of Inventor and your parts and assemblies and how everything relates. This is mainly just to give you a better understanding of what each of these things do and why they separated these things, such as joints and constraints. Okay, so firstly about me, my name is Irshad Hanif. I'm an application engineer with Micrographics. I have about 8 years of experience in CAD design. I've worked in industry before coming into this role as an app engineer with the Autodesk channel. I come from a mechanical engineering background, and my main areas of expertise include AutoCAD, Inventor, and Fusion 360. Right, so you'll also find me being quite helpful in anything regarding CAM, computer aided manufacturing, FEA analysis, design and modeling, as well as your PDM software such as Vault Professional, that sort of thing. Okay, and I'm also a certified Autodesk professional. Okay, enough about me. Let's discuss the purpose of this presentation. Okay, the purpose of this presentation, we want to cover these basic concepts of joining and constraining your assemblies. We want to differentiate between joints and constraints, right? And we want to explore some example situations. I have a lot of templates here so you can see exactly what they do in a specific situation. Sometimes you may read about this in the Inventor manual or the help, but it's not very clear what they do without a visual example, okay? The whole aim of this is to improve assembly creation by designers, because we often see in industry, people are making quite complex assemblies, or they try to make quite complex assemblies, and they end up with a lot of errors with regards to constraints and things conflicting with each other, relationships and constraints conflicting with each other. Oopsie, I think someone new joined and then TeamViewer just popped up. Not a problem. Welcome. Okay. So, before we begin anything, let's just cement a certain concept. We need to discuss what is meant by degrees of freedom before we move on. So degrees of freedom describe the principal ways an object can move in 3D space. So you take any random object. I guess I better move this away. Sorry, another person has just joined. Okay, great. So degrees of freedom. They describe the principal ways an object can move in 3D space. So what does it mean? You take any standard object. Obviously, you have 6 sides to an object in space, and you will see that it can have 2 types of motion: transitional, or in Inventor, what it would be called is translational. Translational movement, which means, in layman's terms, sliding in one of those directions, either X and Y, up or down, left and right in the X direction, or forwards and backwards in that Z direction. Okay, the actual letters of the axes are not important. We're just trying to get this concept of sliding up and down in those 3 principal directions. The next type of movement is rotational movement, which is using the same 3 principal axes, but you can roll about the Z axis, you can roll about the Y axis, and you can rotate about the X axis. So all in all, 6 principal types of motion for any object in 3D space. Very important to get that concept down. Sounds simple enough, but they will refer to it a lot in your joints and constraints. Okay. So joints versus constraints. What's the difference? Well, okay, so a constraint removes your degrees of freedom. So we just spoke about degrees of freedom, and we said that it can either slide up and down, left or right, back and forth. A constraint will remove those and between 2 faces or 2 edges, or basically 2 bodies of your assembly, and make these components positioned relative to each other. Okay, very important. It removes the degrees of freedom and makes them relative to each other. Joints, however, will allow you to custom position components and define each of those degrees of freedom. Now, in the next couple of slides, we'll discuss exactly what kind of basic templates they have for defining those degrees of freedom, but it allows you to, for example, say, okay, in the X direction, I wanted to rotate, and I only wanted to move in the up and down direction, for example. Okay, so that's the key difference between the two. One will remove the degrees of freedom, the other will allow you to define them. Okay, so let's just take a look quickly at all the different types of constraints. You'll see when you use the constraints block in Inventor, you will find you have mate, okay, which places 2 faces on the same plane. Pretty straightforward. We'll take a deeper look at it when we get to the live section, but we'll take a deeper look at all of these types of constraints. Then we have angular, which allows for angle between 2 faces. So not on the same plane, but there might be like a 20-degree angle between one face and the next. So that might be a thing you want to do. Tangent allows a circular face to attach to a flat surface. So, you know, this the circumference of a cylindrical face, you can make it always constrained to a particular flat surface. Okay. Insert is basically a combination of it's a combination mate of cylinder type mating and also mate with a flat surface. So it'll basically ask you to choose a flat surface, and it will detect a perpendicular cylindrical mate. I'll show you exactly how that works in the demo. Okay. Lastly, we have symmetry, which allows a consistent symmetry or consistent distance between 2 faces that you may select with a reference plane. Okay, I also have an example of that, and we will show you how it's useful. Okay, now let's discuss joints, and we will take a look at all the joints in the joint dialog box, which you see up there. Okay, so you're going to have rigid, which removes all degrees of freedom. Okay, so it's just basically cementing that component in where you slot it in. Okay, so think of a welded joint or bolted joints. So if you have 2 things that are bolted or welded together, that's basically what I do. It can't rotate in any direction. It can't slide back and forth, up and down, nothing. Okay. Then we have rotational type of joint, where one of these axes, either X, Y, or Z, will be able to rotate. Everything else will be fixed. So the other 2 axes will not be able to rotate, and the other, it will not be able to slide in any of the 3 axes. Okay. So think of a lever arm. It will just be able to rotate in one direction, and that's about it. can't move back or forth, up or down, right? Then you have a slider, which has one translational. So just like how the rotational joint had one rotational movement, a slider will have one translational, mean it can either move simply back or forth, or maybe simply up or down, or maybe left to right. Just one of those translational degree of freedom, right? Then let's jump to the next three. You've got cylindrical, which is basically a combination of slider and rotational. So if you think of something like maybe a piston or an actuator which has a rotational and a sliding mechanism, it can slide in and out of a cover, as well as rotate about that same sliding axis. So you can, that's why I put there an example, a screw, one translational axis and one rotational degree of freedom. Okay, then you have planar, okay, which is two translational, and the third direction will be a rotational. So if you think of a chess piece on a chessboard, okay, you'll know that the base of the chess piece slides in the X and Y direction of your chessboard, and then it can also rotate about the other direction, which is the Z direction. So about its own axis, it can rotate there. So a chess piece is on a chessboard is a very good example of the planar joint. Okay, and finally the ball joint is simply where your translational axis, meaning sliding up, left, right, or down, is locked, and only the rotational axes are open, which means it can basically rotate in place like a ball, hence ball. All right. Right. The last option you have there, or actually it's the first in the box, is automatic. You'll notice that it will always try to give you an automatic joint, and what it does, it detects, I seem to have missed out the D here, it detects based on four choices. Okay, so rotational, cylindrical, ball, and rigid. Actually, these are supposed to be two separate. I don't know why they came there, but rotational, cylindrical, ball, and rigid. Those are the four principal types it will detect, and it can detect a combination of the two. Okay. So that being said, let us jump into a live demonstration. So I'm just going to try and quickly switch to my Inventor if I can. And we're going to look at some principal relationships. Okay. So actually, I shall just delete this to begin. So we have two blocks here, and we want to start by discussing basically your constraints. So if we look at we want to place this block in here, we can look at our constraints dialog box, and we'll be greeted by what you saw up there. We have mate, angular, tangent, insert, and symmetry. So we'll start with the simplest one, and we will look at mate. So mate will allow you to rigidly fix. Remember, we said if you go back to our slides, we'll say that the rigid removes all degrees of freedom and just cements it in there. So for example, I want to mate that base with that base. I want them to be fixed in line. So for example, I will click on that one and that one, and you'll see I have two solutions. I can either make them face each other, where the two faces I click will face each other, or I can make them flush where they face in the same direction. In this case, I want it to be flush, so I'll use that. All right. And then I can mate maybe that one and that one in the same direction. So you'll see it'll adjust those two. I'll click apply, and perhaps that one and that one. Okay, I've got enough. That was my mistake. But basically, we'll be able to, let us say, put, I should have done it the other way around. Let's do that again. I'll start from here. So we'll make that and apply there. I'll use these two in the same direction using a flush. And I will do the same with these two. And so I've put my block in the way. So sometimes the order matters if you do it in the wrong order. But basically, you've used your mate. Right? So basically what it does do, it asks you your first and your second selection, and it gives you a method of solution. You can also create, for example, an offset. So if you go to all of those, remember, all of those constraints live down here in your relationships. So I've got a flush, and a mate. So let's say, for example, that particular one where you want to give it an offset to go in that way, you can sort of give it an offset of, let's say, maybe 10. Okay, it does give you a shortcut to offset it there. Of course, you can right click and go there to edit and use this little box here where you can adjust it and see it in real time. So it'll move it off from there. Okay, that's basically your mate. The next type is angular, and I think I have a different one to show you here. So in the previous example, you wanted to do one where they were along the same plane, but here you want perhaps an angle between these two faces. So let us try and constrain. Maybe we'll use the angular function, and we'll give it and we'll choose the first type of option. So you can see it uses a reference plane using that as 0, 0, and we say, well, we can give it an angle between them. Okay, there's a couple of methods of solution. There's direct angle, where you can define the directed angle, undirected angle, and explicit reference vector. If you choose that, you'll be asked for 3 inputs, but if you choose these, you'll be just asked for the 2 planes that you're trying to calculate about. Okay, I'm just going to rush on and move to the next ones. Okay. Okay, tangent will allow you to put a circular thing on a circular surface on a flat surface. Insert will allow us to put in something like a screw. Like we said in the slides, it is a combination of your mate with a cylindrical surface. So let's just take a look at an example for that. I think I have one here. Let me just find it. Oh, here we go. So like I was saying, if we wanted to use a mate, normally I see people in industry, they will do this. They will simply choose their mate and they will go, right, I need to mate that top end with, let's say, there. And then they've got to do apply, and then they've got to do another mate, and they say, okay, that one goes in there, which works, yes, but it's a lot of steps. That is why we have the insert. What the insert does is it allows you to do that particular type of action in one shot. So you choose a face, for example. Let's put the washer in first. We will choose that, you see that circular highlighted face and that cylinder center will mate with that. So in one shot, it's aligned it with the center as well as fix the face. That's the benefit of the insert. So I'll do it again now, this time with the screw, and you see how much more easier it makes it in one shot. So now I'll just got to choose the face that I want. It automatically picks up the cylindrical axis as well. And then you'll see all I've got to do is click either that one or that one, doesn't really matter. We just need to tell it which face to mate. And it fits it in cylindrically in one shot, right? You can also do this with, for example, the cover. You have an edge that you want to mate with the cylindrical center. You can do it here and there, for example, and you've placed your cover on in one shot. So very useful. Okay. Lastly, you'll notice that you have the symmetry. And I think I have a design here to illustrate that. Here we go. So you can see in this design, I've got some constraints. I don't know if I was supposed to. Let me delete the one that I've already done just to show you how it was working. Okay. So you'll see here that as I pull this out, I actually want the other one to pull out in the same direction away from this reference point here. So currently, as I'm doing it, it's just moving this screw on the number 1 side. I want number 2 side to also move in the same direction. Okay. Oops, sorry. So what you can do is use a symmetrical constraint. Okay, and you can click those two. And then, of course, it's asking for a third input there, which is the reference symmetry plane. So if you click that, you'll find that it does this. So now I can escape. Now when I pull these two, it keeps them the same distance away from my reference point. So that's an example of where you would want to use symmetry as your constraint. Okay. Now we can move on to, I think we can move on to joints, and we'll take a look at this example and show you why joints are better. Okay, because remember, if you put in a joint or if you put in a constraint using your normal constraint, it can sometimes take a lot of time and you're not able to control your degrees of freedom. So for example, I'll show you the difficult way of working, where you've got to constrain these in the same direction. So it does allow you to do that there, but then you've got to go in and you've got to say, okay, well, this mates with that and that mates with that, etc., etc. It's quite a tedious task, say if we go like this. We can use the insert, and we can say, oh, I think I've already done. Yeah, sorry. We'll just get that right. And I'm supposed to be able to, of course, it doesn't work during the demo. I think I've already added some things in there. Let me just delete that. But basically, it's going to take you a lot of time. And you can see I can insert in another constraint here. Let's do that. And I will do, there we go. I think TView is just messing with my mouse here. So you can see I can do a mate. Now you'll notice that I have some tabs in here, which I've never discussed before. Okay, I can give it some motion. I can give some transitional type of solution, but we're not going to discuss this in this webinar. That's beyond the scope. I just want to show you how the constraints and the joints will work. Okay, but basically, because I've added a mate, this is now fixed. Okay, so, oh, sorry, TeamViewer is just messing with my mouse. I'm just going to go here. I do apologize because of the live recording, the mouse doesn't work properly. Okay, I'm just going to try one more time. Okay, and now I'm going to try and oopsie. Right. So the problem is, like I was saying, that is now rigidly fixed. And you want to have some You'll see here, it allows you to rotate that. However, if we wanted to do some joints, let us discuss a new example using joints. Okay, so what I can do with joints is, instead of removing all those degrees of freedom, I can have either a rotational, slider, cylindrical joint. So let's just take a look at the difference between all the types of joint. So rigid is basically, let's say that base, and you'll see it does a little animation of what it's fixing to each other. I can click play here on the animate. It doesn't move in any direction because, as per the definition of rigid, no translation in any axis and no rotation in any axis. Okay. However, I can also do rotational, where it will allow, you see the direction there, it will allow rotation in that particular axis. Okay, I can also do a slider. Okay, this might not work very well because, okay, I've chosen two planes that are not, but you can see it's allowing, or it's rather detecting, sliding in one direction. Although this is not ideal because it's using the planes that I selected to slide either up or down or maybe left or right, and not the cylindrical plane. If I really wanted to insert this in, I would of course use the cylindrical setup. So what is the cylindrical joint? The cylindrical is a combination of rotation in one axis and slide across another axis. And you can see it's doing exactly that. I've chosen that plane and that plane. It's rotating about one axis and sliding along a perpendicular axis. It will detect automatically which way to slide. So if I play that again, yeah, just bear with me. TeamViewer is slowing down the mouse and recording. I'm not sure if you can see that clearly, but that's basically what it did. Okay, so we will leave that like this. We'll come back to this example. I just want to show you, actually I should show you slider. So here's a good example of where you'd use slider. Say if I wanted to create a joint on that surface, remember I can hold control so it fixes onto that base. Click there. It's important to define the exact point where you want it, so that I'll hold control and click there. So you'll see that the two faces that you click, that's the plane that it will slide along. Okay, you can also set some limits. I'm just going to apply it for now, just to show you that it indeed has created a sliding constraint. And if we go here and we wanted to edit it, right, I can also set its limit. So if I wanted to stop at where the red face meets the red face, I can go and control its limits and say, you'll see there's two options in here. One is grayed out because it slider doesn't have any angular movement, but it does have linear movement. So I can say start at 0. Its current is whatever it is, and it must end at, I'm going to just estimate and say somewhere there just to show you, let's say -60. Okay, so we'll see that we can, so with our joints as compared to our constraints, we are allowed to define not only the limits of the not only the motion, but the limits of the motion as well. Okay, the next one I wanted to show you was planar, and I did use the example of a chess piece, and we said we can use that and that, and you can see that 2 degrees of translation, and it can rotate about the third axis. Neither of the two translation axes, it will use the third axis, the one that is not using for translation, to rotate about. Okay, so there we go. Our horse can move around and it can also rotate. Okay, our knight. Okay, but the last one is ball. And like we said, this is a good example to show you the ball type of joint. It's not going to be able to translate in X, Y, or Z, but it will be able to rotate in all of those axes. So we can choose the ball type of a cylinder. Remember, you can hold control to finally pick the right position. Okay, and it'll be able to move about in all or rotate in all three directions, but not translate in any of the directions. Okay, so now you would notice that I have fixed it, but I do have a problem. I am now cutting through the plastic here, whereas you only wanted to be able to rotate this way and that way and go through these little slots. So what we can do is we can click these two objects and we can create a contact set between them. You'll see you get a little logo there that says contact set. Then you can go to, I think it's the inspect tab. There we go. And you can activate contact solver. So because you've created a contact set between these two objects and you activate contact solver, it will detect where and where it can't move. So now you'll see that I'm not able to move in any direction where it would clash with the black casing. So you can see it's guiding me straight through the slot and also allowing me to move wherever I wanted to. So I'm not sure if any of you are aware of that, but that's a very useful tool when you're using joints. Okay, and that was basically it. So I will go back to our example. I'll do the same thing again here. Okay, so we've inserted a cylindrical type of joint, whereas in the previous one we did a ball joint. Okay, and I'm going to use the limit as well as contact solver. So let's go and let's just, we'll see here that we can extend far too much. So let us just make a limit from there and there. So we can go limits. So we can set a limit for its angular rotation, because remember, this is a cylindrical joint. So it does have a rotational aspect to it. So we can say a start will be, let's just see where 0 is. And its current is whatever. And let's just see, I'm just going to estimate 60. Because I don't know what is the starting point, because I've moved it too much. But I think, yep, that's it. That's the limit there. And I've limited it to 60 degrees. I'm not exactly sure what that angle is. Probably is greater than 60 degrees. So we can just go and edit it there. I'll make it, let's say, 70. Let's just see if that gives us a little, there we go. That looks a bit better. Although I would say 70 something or 60 something would be better. So now we can only move between there and there. However, it is still cutting between the two. That will solve with the contact solver. The next thing we just need to do is limit these faces so it cannot go further than this. So go here. We'll try and estimate just to get a bearing of where it is. And we'll say the limits. Okay, so the current is -2, so I'm guessing it's a little bit in there. So we'll say we'll have a start of 0 and an end of, let's say, I'm estimating the distance between there and there. Let's say 50 or -50 rather. Actually, in this case, there probably doesn't need to be a limit, but it's supposed to be positive in the other way. Okay. There we go. So I would estimate that to be, let's say, I suppose I can just measure it, can't I? Let's just measure that and that. So that's about 160. So we will give it 160 in our motion. Okay. That's better. I forgot to account for the radii of these limbs. Okay, so that's good. Now all we got to do is, remember when you're using the contact set, you got to make it so that it doesn't touch. And I will say, okay, between that component and that component, we want to enable a contact set. And we want to go in and inspect, activate contact solver, and it is. There we go. So you'll see it's not allowing me to move unless I am not making contact. And that's it. We have successfully used joints, limits, and contact solver to create an intelligent assembly. Okay. Okay, so Han, yeah, the video will go up on YouTube. We will send links to you if you need. Sure, now I understand about the lag. We will send links to the YouTube video for this webinar. Okay. But I hope you caught it now, because I did do it again. But anyway, I think this brings us to the end of the webinar. I'm just going to you can see my details up there on the screen. That was basically a short discussion about joints and constraints. You're welcome to take down my details, or if you are making assemblies and you have any questions regarding this, or basically anything in Inventor, you're welcome to contact me. You may ask questions if you have any at this point. I'm just going to leave the floor open for a few minutes. You may type in questions. If not, that's the end of the webinar. Okay, thanks for joining, everyone. And we will see you in the next webinar.